and I'm talking about anti-fragile software, and this is a new topic for me. It's the first time I've presented it, so I'm looking as much for your feedback and ideas, because this, I think, is an area in the industry which is in formation rather than something that's a polished thing that everyone is doing already. So I'm looking to get your input and ideas on this, both here at the conference and afterwards. I've got my contact details at the end. So the first thing then is why are we even bothering to think about fragility of software? Well, ultimately, for software to be used, it has to provide some sort of value to the users. But as we all know, software can fail in use. And when it fails, it could degrade the experience for the users. So we want to find ways to cope with that and adapt the software so that even if something bad is happening in the environment around the software continues to provide some sort of value, albeit it may not be as much or as good as we'd want it to do. So perhaps from a web example, if people disable JavaScript, we don't want the web application to fail entirely. We want some sort of behavior that still allows people to do things like place orders, do searches online, rather than simply failing and saying error, no JavaScript available. We have many, many causes for these problems, particularly when working in larger scale software systems. For instance, where we're assuming that a version of a library is one version and actually the version has changed, but the software doesn't detect that a change has occurred, then we could have problems in the behavior of the software, which our software may or may not notice. And if our software doesn't notice, potentially that adversely affects the behavior from the user's perspective. So what do we want our software to do? We need it to continue operating. Perhaps it'll operate in a simpler mode. Perhaps it'll change the algorithms it's using. Perhaps it'll reduce the accuracy of the information it gives us. Perhaps it simply gives us back an error code quickly. For those of you who've worked with web, and I assume that's most of you, you're probably familiar that there are error return codes that come from every HTTP request. There are the 100 return codes, which says basically I'm doing something, please wait. The 200, which is essentially an OK. 300, you've done something that you may be able to, the system has got a problem and is to change something like a redirect, so 301, 302, 303 redirects. The 400 error code says that you have done something wrong. And paradoxically, when it's a page not found, it's basically trying to say that I can't do anything about this, you need to do something about it. And the final class are the 500 error codes, which are the ones that says the server has gone wrong, something is broken here, please retry later, or whatever it is. So when we have systems that are overloaded, we may want to return back something quickly, like a 500 return code, rather than trying to process that request, which may then further damage the system from our perspective. It may affect many users instead of just the one user who's got this request. So we're looking for ways to do this in software. So simply, fragile software then is software that can fail or is rejected because perhaps our users reject our software because they don't agree with its behavior. So it's these sort of coping strategies. We're not necessarily changing our code, we're changing the system level, a larger level. So we're looking for ways to do this in software. So simply, fragile software then is software that can fail or is rejected because perhaps our users reject our software because they don't agree with its behavior. And anti-fragile software is software that's still useful for our users. That's what we're looking to achieve. So in terms of prerequisites then, I've got two categories. I've got robustness, which is where we're looking at retaining the availability of the software. It continues to answer requests, albeit it may answer it in a degraded mode. And we're looking for integrity of the software. So if there's something going wrong, we don't want to lose the integrity of the system, which could be things like the connections between records in a database, or in terms of transactions, the acidity of transactions. And acidity is the ACID acronym in terms of the behavior. So we want the transaction to perform totally or not at all as if it never happened, rather than having a partial transaction occurring. And then we need the resilience of the software, so being able to cope when failures occur and just essentially cope with the adversity without failing entirely. One of the big problems with software that hasn't been well thought through is the error percolates up to the top and the user sees the error message, the stack trace. And this is the sort of thing that gives an adverse behavior. Clear the software is no longer coping, it has failed. So one of the things we can do is look at ways of having coping strategies for that. So some coping strategies then, one is to improve the robustness, and one concept is load shedding. And load shedding says if something's going to put too much load on me, get rid of it, and get rid of it as quickly and efficiently as I can. So rather than having something go all the way down the stack, you may have something as protective code that says this request, get rid of it, just send it away, rather than doing anything more with it. If in doubt, get rid of the request. The second one is to improve the resilience, so capturing and redirecting the errors. In Java, we've got the uncaught exception handler, and typically if you're adding some sort of library in that captures the exceptions and sends them to you, it's using this handler as a way of saying, if all else fails, I'll handle the exception rather than the application being quit or failing at that point. We may want to improve the checking, so one of the things may be that we actually add fields such as a version number in a protocol, and we check the version number and say, are we getting the version number we expect? And if we are getting the version number we expect, then we can continue operating. If we get a different number, then we know that one of our expectations is not being met in the software, so we then want to deal with that mismatch expectation and perhaps reject that request and do something differently. Perhaps it's a message to the system operator saying, it looks like this computer's malconfigured or we've been pointed to the wrong servers, please go and fix this problem. Meanwhile, returning a nice message to the user who's asking us to do something, saying perhaps the system's temporarily unavailable or this service is not available, whatever it is, so dealing with the user side and also notifying the people who are operating the systems to fix the problem. We may want to put guard code in. So sometimes we haven't got the option of fixing the broken code, the vulnerable code. What we do instead is we put something in front of it as a sort of sacrificial layer, and that is what deals with it. And typically, if we're looking at large-scale internet systems, they'll have defense in depth, which says that perhaps the firewalls will look at the transactions coming in, the requests coming in. If they see something that they believe to be dubious, the firewall will reject it to protect the server behind it. To give you an example, if we're looking at, say, C-based code, and we've got a buffer overrun condition because the string is too long, it would be rejected by the firewall. We don't need to fix the problem immediately in the server code that has the vulnerability. So it's these sort of coping strategies. We're not necessarily changing our code, we're changing the system level, a larger level. And the one you're probably all familiar with from writing software is putting some sort of timeouts on calls and saying, rather than wait indefinitely, I want to stop at this point and then recover from the problem rather than just allowing it to hang indefinitely. Now, I think Naresh has joined me. This talk actually came out of a debate with Naresh saying that potentially agile software development practices in the industry might actually be increasing the fragility of code of the software that we're working with. So this is the hypothesis we've got. I've taken two perspectives, one from a lean perspective, and the next slide is from an agile perspective. And this is part of what I'm hoping to open up for debate, especially since I suspect all of you have heard of agile and lean, and you may have your own perspectives on how that improves software. Well, here's the sort of counter-argument that says that maybe it's the other way around. So the first is that we have this minimal viable product. So it says, don't worry about creating the whole product, do something small, tiny, hand that over and see if it's good enough for people. Well, when we're doing this, then we're not necessarily considering the resilience or the robustness of the software. We're saying, let's just give you something and start working with it. And I've very, very seldom seen anyone put anything in the requirement saying, let's look at robustness, let's look at error handling. It's normally a positive story saying the user's allowed to book a holiday online. Okay, well, what happens if the other system's not available? It isn't really considered at this point. The second adage is the dry principle. So don't repeat yourself. Only write one piece of code. Don't write alternatives. Now, this is a good principle generally. So rather than having 3, 4, 5 potentially mismatched implementations, we only have one of them. But sometimes there's a lack of alternatives, and we may be considering something to be the method of doing it, but again, it hasn't got the resilience or robustness built into it. And that's part of the satisfying side of it, which says it seems to be satisfactory, we can move on. So let's not worry about spending any more time or energy on this method or this feature or whatever it is. Let's move on and do something different. Let's add a new feature rather than going back and cleaning up the code base. So in terms of the agile development practices then, the minimum viable code, this is my words, but if you've been familiar with test-driven development, you say, well, basically I write a test first, and I write the minimal implementation, return 0, and see if the test passes. If the test passes, then write another test as a failing test, and then check the algorithm or whatever it is. But we may stop that process prematurely while we're still thinking about positive cases, rather than thinking about negative cases. A friend of mine's company, he's a pretty good developer, but he had a problem because he didn't validate a date of the 1st of the 1st of 1970. Now, for any of you working with Unix, that is the beginning of time from a Unix systems perspective. And what happened is that that call was passed to an API. It came from a hacker, by the way. The hacker was trying to break into the system. And so he got a timestamp of 0. And it went to the API. And the API returned a different type of return because of that value. Because no programmer actually thought about a date of the 1st of the 1st, 1970. Most of us are thinking, well, it's 2014. We'll never get a request for anything sooner than 2014. So we don't even think about the test cases for what is a valid date, but not one that we expected. And we eventually had to fix the system because the hacker had actually broken in and corrupted the database through that sort of attack. So it can be quite serious, just this seemingly innocuous thing. But we're unlikely to be thinking about that. And we tend to have a bias, especially from a development perspective, of working code. Can I show that it works rather than can I prove that it's broken? And then the time boxing concept says that we're working to a sprint or an iteration, seldom longer than a month. So once we've finished, we believe we have finished. But sometimes the problems appear later on. It takes us so long to get back to work on that code again. Meanwhile, you're working on another task. You've been assigned something else to work on, so we're not going back to revisit that code base and from there fix and improve the code. So here's some suggested coping strategies. They're not the only ones. These are just ideas at the moment. So the first is the defensive code that makes sure that it has things like a whitelist rather than a broad acceptance. So a whitelist says, I'm only going to accept these things, everything else will be rejected, rather than having a blacklist says, I'm going to reject these things and accept everything else. And in APIs, you may be looking at implementing APIs saying, I only want to accept these valid calls and everything else will be rejected with some sort of error return. And that's a good way if you're dealing with versioning of software, that you're changing the underlying APIs that you're relying on. If they're returning you an error, at least you know something went wrong. The next thing is designing in recovery mechanisms, and we may need to design them into the code so it recovers from a call that fails. So we call the server, it gives us back an HTTP 500 error. But we may also want to look in terms of development practices. So we have some way of coping when we get feedback from the field that we can allocate time to work on the problem, address the problem now rather than waiting until the next sprint or whenever it is that we're allowed to work on it. So both are important. And perhaps using the feedback to help improve the testing practices. So perhaps we missed a class of problems because we weren't thinking about it. Well, unless we actually consider how to improve that as well as development, we may be caught by the same sort of problem in future. When we buy a computer, particularly the ones that are running in the data centers, we tend to be using something called error-correcting memory. And error-correcting memory says that we put extra memory chips in the computer, and they're used with some sort of checksum algorithm that says that if there's a failure in the memory chip, say a single bit failure, we can detect that. We can detect any single bit failure, and in some cases we can recover from that because we have extra redundancy encoded with the byte. Now, similarly in software, going back 30, 40 years, in our data communications protocols, we had the concept of some sort of checksum, and these days you're probably all familiar with MD5 hashers as a way of validating content and saying, well, we'll check the hash or the digest, and we'll say, based on that, we'll assume that the rest of the content is correct. So putting things like this into designs of protocols may help us to detect the problems, and in some cases recover from the problems, rather than just assuming that the result is correct that we're getting. What else do I want to do? Machine learning algorithms. So this is, I think, fairly conceptual rather than in practice. So most antivirus software seems to be sold with these intelligent algorithms. You know, it'll sort of work out what's happening in the virus, it'll adapt itself and dynamically improve itself to defend against similar problems in future. I'm not sure that really holds true. They certainly continue to ship updates to antivirus software, which I assume is because they found problems. So they're changing the code at development level rather than the algorithm self-adapting. but potentially machine learning is a concept that as it detects types of errors, it says, I'm noticing this seems to be causing problems to the system, so I'll adapt myself and improve myself because of that. From an engineering perspective then, so rather than just a coding perspective, looking at things like failure analysis and failure mode effects analysis, FMEA, is a fairly well-established technique going back probably 30 or 40 years of saying we look at each failure and we say what caused the failure and can we address the cause of the failure or at least address the symptoms of the failure. Providing fault tolerance, again going back a long time in the industry, there's this computer company called Tandem. And Tandem made computers called Tandem non-stops, and in software they found ways of detecting problems and always fixing and recovering from those problems so that the overall service didn't go down. So you find ways to look at that. And finding ways to recover, because when something goes wrong, we have ultimately to recover from it. Anyone from the US here? Okay, one. Do you remember the brownouts in America, the power failures on the East Coast? Yes, and do you know what the cause was? Okay, I can't hear you actually very well, but there's several things that happened. Basically what happened is I think the whole East Coast lost power for about 3 or 4 days. And the typical problem happens, a tree in bad weather falls on a power line, the power line shorts, and a system then copes with that. So it turns off power to that area, which is a small area, maybe a town or something. But what ended up happening is a number of errors came into the primary server, and as they came into the primary server, it became overloaded and it failed, it crashed. The design of the system was that you had a primary server and a backup server, and every message that came into the primary server was replicated to the standby server. Does that make sense so far? So the primary server doesn't cope, but the standby server gets the message. The failure mode was they were running the same software. So what crashed the first server simply crashed the second server about half an hour later. And it took them 3.5 days to recover from that, because those servers controlled the power for a large area of the US, and you had all the overloads percolating through the system. So this is the thing that's saying we need to think about recovery mechanisms. The old Microsoft Exchange server from memory had a similar problem. It had a sort of master-slave relationship. And the problem wasn't that the master failed and it went over to standby. The problem was how did you get back from a standby being primary to the master being primary. So it wasn't the initial, this one goes down, sorry, and this one takes over the load. Is how do we get the two back in sync again afterwards? And that took many, many hours to recover from. So it's these problems we're trying to look at in terms of the recovery. Dependency injection is, from my perspective, when we have code, we pass in the inputs it needs that it depends on to operate. And we can then write more effective tests for that code, rather than relying on external inputs coming in from method calls and things. So we actually pass the inputs then, and then process the information from there. And this is all part of the choices of software design and implementation that can affect and improve the implementations. Here are some further reading for you. A little bit of hardware, but nonetheless it's good software involved. These are academic papers, so Sigmetrics is looking at metrics of computer systems. And we can similarly see some additional papers with this. A book I only heard about today, which is the guy who wrote the Black Swan book, which you may be familiar with, has written a book called Anti-Fragile. So I'm just starting to look at that. And the next one I'm going to give you an example of is a Wired article about the Google Loon project. Has anyone heard of the Google Loon project? A couple of you? So the Google Loon project is basically to provide internet to another billion people by floating up balloons into the sky at about, it's going to be about sort of 18,000 meters, 60,000 feet. And when they started doing the project a year ago, which is what this article is about, basically the balloons kept bursting. They'd go up, they wouldn't work. You know, they would fail within hours or days. And people sort of laughed at Google and said, you know, what the heck are you playing at? How's this ever going to work? It's never going to stay up there. But what they did is essentially, every time something failed, they analyzed the failure, worked out what was going wrong, and through that they found ways to stabilize the system. And now they've got balloons flying up there for 100 days and circumnavigating the globe many, many times. So it's an engineering practice that says, we start from the beginning, we know it isn't going to work, but we adapt and improve our processes. So we end up with a system that's less fragile. It's something that's robust and reliable in future. So I've got about 5 minutes, 6 minutes for questions. I don't know if there's a roving mic or anything, is there? Any organisers? If not, I'll try and repeat the questions. So I know there's 5 minutes left. Does anyone have any questions for me or any thoughts on this talk? You smiled, so any questions from you?
No, I smile because you rarely get questions.
Thank you.
You rarely get questions.
Okay. Well, I had a few on my first session, so come on, you've got 5 minutes on the camera otherwise.